Record. Okay. Okay, so today we're going to talk about linear and angular speed, which is moving on a little bit from what we did yesterday, but it's using the kind of ideas we were talking about. So essentially linear speed, which is the kind of speed that a lot of us are familiar with, is length over time. It's when we talk about miles per hour or meters per second or feet per second. In general, it is length over time. Any length, any linear distance divided by time, it gives us something called velocities. In other words, you may have heard if you've taken a physics class, that is linear speed. And then angular speed is a little different. Instead of talking about a length, as in like feet or meters or miles, we talk about an angle. So we would talk about like 60 degrees per minute or a number of radians per minute or radians per second. We can also talk about revolutions, which is just if we have a circle, we think about going around the circle once as being a revolution. The only difference, you can think about linear speed being like distance and angular speed just being like an angle. So you can think of how like angles compare to an arc length as we compare angular speed to linear speed. So let's start with an example on angular speed. So let's say we have a 6 centimeter DVD, which means that its radius is 3 centimeters. And we're going to put a dot 1 centimeter out from the center and a dot 2 centimeters out from the center. So let's draw that real quick. Here's our CD. We know its radius is 3 centimeters. We're given that information, and then we're going to draw a dot 1 centimeter out. And then we're going to draw another dot 2 centimeters out. Okay, and when it is rotating at 10 revolutions per second, it gives us an angular speed. How many radians per second are the two dots going? So essentially, our task is to convert revolutions per second into radians per second. Well, how do we do this? We know immediately that one revolution is one complete circle. That's just by definition, a revolution is going around a circle one time. How many radians are in one revolution? Well, we know that one complete circle is 2 pi radians. So that gives us that one revolution is 2 pi radians. And we don't have to write units here, but I'm just going to write radians to be extra clear. Okay, so we know just right off the bat, the information we're given is that this CD is rotating at 10 revolutions per 1 second. And all we want to do is convert this unit right here, revolutions, into radians. So all we have to do is make the units of revolutions cancel. Just from this little piece of information up here, we know that for every 1 revolution, which I will put in the denominator because I want revolutions to cancel, we go around the circle 2 pi radians. And I'm just going to write radians in there just to be extra clear with what we're doing, because we're doing a conversion. Units of revolutions cancel, and we're left with 10 times 2 pi, it's 20 pi, and then we're left with units of radians per second. And notice that all we wanted was radians per second, so we are actually done here. Notice it didn't matter. We didn't use this information. We didn't use the information of where the dots are. Regardless of where the dots are, our angular speed does not change. And it makes sense if you think about it, right? If you're holding a CD with 2 dots drawn on it, when you spin it around, once you make it a full rotation, the 2 dots are going to make that full rotation at the exact same time. They're both going to complete their rotation at the same time because it's not dependent on how far they travel. It's just dependent on when they're done making the full circle, which they will be done making the full circle at the same time. So in general, for angular speed, the radius of our circle does not matter. It doesn't matter at all because we're just talking about how quickly things complete our circle. This is counterintuitive because we think, that the size of the radius we're working with would matter. And that's a good intuition because for linear speed, it will matter because that's talking about distance, and the size of the circumference depends on the size of the radius. However, when we're just talking about how quickly dots make it around a circle, we don't care how big the circle is. They're the dots, no matter how far out they are from the center, they're going to complete the circle at the same time. Are there any questions on this idea of angular speed? And we'll get practice with a little more, and you'll get some handy formulas here in a second. But before we move on to that, we're going to talk a little bit about linear speed, which is the one that we're more familiar with, probably new in the context of circles, but having knowledge on this already will help. Okay, so let's consider the exact same 6 centimeter DVD. It has a radius of 3 centimeters. I will just draw this oh, that's the highlighter. I will just draw this picture again. Same CD, radius of 3 centimeters. Draw our dots 1 centimeter and 2 centimeters out. One right here, one right here. Okay, so say we're holding this DVD in our hand and rotating it 1 complete rotation. How far did each dot travel? We are not talking about how many revolutions per second. We just want to know if I just rotate the CD 1 time, how far did the dots travel? Well, what we're talking about here is circumference. If you think about, let's look at this 1 centimeter dot. Traveling 1 complete rotation would mean following this path. And for the 2 centimeter dot, traveling a full rotation would mean following kind of this path. So it makes sense that the answers for these would be different. And we're essentially looking at circumferences of different circles. So the key for what we're going to do here is the formula for the circumference of a circle, which is just 2 pi times the radius. Okay, this is going to be our key here. Just make a note that this will be our key for conversion. Okay, first let's focus on the 1 centimeter dot. Essentially, if we think about this little circle here and this path it's going to create, we're thinking about a circle that has radius of 1 centimeter because it's 1 centimeter out from the center. We're not thinking about the CD being 3 centimeters at all. We're just thinking about the smaller circle that the dot with 1 centimeter will create when it's rotated around. So to find the circumference of this, we just get that the circumference is 2 pi times 1 centimeter, which is just 2 pi centimeters. And so because it traveled 2 centimeters or 2 pi centimeters in 1 revolution, the linear speed of the 1 centimeter dot is that it is going 2 pi centimeters per revolution. Because the revolution we're talking about is just 1 circumference. That's all it is. The revolution part of it here is just the circumference. And we're knowing by this information, for every 1 revolution, we're going 2 pi centimeters. Cool. Similar idea for the dot that is 2 centimeters out from the center. When we rotate the CD around, it will go in a circular path that has a radius of 2 centimeters. So to find the linear speed here, we know that the circumference is 2 pi times 2 centimeters this time, which is equal to 4 pi centimeters. So similarly to last time, we know that the dot that is 2 centimeters out from the center is traveling at a speed of 4 pi centimeters per revolution. It makes sense that this one's traveling faster, right? It's a little bit further out, so it has more distance to travel to go all the way around the CD than the 1 centimeter dot. Because if you draw a dot super close, it doesn't have to go very far, whereas a point on the outside of the CD would have to travel all the way around, which is a lot bigger of a circumference. Okay, let's tie this back into our old example a little more. If the CD is traveling at 10 revolutions per second, what speed are the dots going at in centimeters per second? So essentially, we want to convert revolutions per second to centimeters per second. In other words, we want to compute revolutions to centimeters. Turns out these 2 pieces of information here give us all we need to know. So let's start with the 1 centimeter dot again. So we know that the CD is traveling at 10 revolutions per 1 second, and we want to convert revolutions into centimeters. Hey, conveniently, we have a conversion up here that is already in a relationship between centimeters and revolutions. Amazing. So because we want the units of revolution to cancel, we want that to stay in the denominator. So we know there's 1 revolution for every 2 pi centimeters that the dot travels. Units of revolution will cancel. And we know that the dot that is 1 centimeter away from the center is traveling at 10 times 2 pi, which is 20 pi centimeters per second. Similarly, we can do the same calculation with the dot that is 2 centimeters away from the center. This stays the exact same because that is just the angular speed. We're talking about how many revolutions per second that we are rotating the CD. So this is just still 10 revolutions per 1 second. That doesn't change based on the dot. Now, instead of this piece of information here, we use this guy. So instead of 2 pi centimeters per 1 revolution, we are going 4 pi centimeters for every 1 revolution. Units of revolution cancel. 10 times 4 pi gives us 40 pi centimeters per second. And notice that in pretty much all of these calculations, I'm just leaving the pi alone. I could plug it into my calculator and find out what this is, but this just looks a lot nicer than a decimal because whenever we evaluate pi in our calculator, it's not going to give us a nice number. And B, there's no need to. This is exact. You can do decimals if you would like. However, in a lot of cases, it is just nicer to leave the pi there. So if you notice me doing that, that is why. Are there any other questions on this example before I move on? Okay. So now that we've talked about these, there's actually some handy dandy formulas for angular and linear speed that we were just using without even really realizing it. So angular speed, this guy right here, it looks like a W. It's actually the Greek letter omega. It is a lowercase omega. It is the last Greek letter of the alphabet, I believe. So that will commonly be used for angular speed. It's just written like a curly little W. But angular speed, we will always want in radians over time. We want the top guy to be how many radians we're traveling. We could do degrees. We could do revolutions, but whenever we're relating angular and linear speed, we need things in radians because it just makes life nicer. It gives us a nice relationship between the radius and the circumference. Radians are just really nice to work with. So we'll always want this in radians over time, which I just denote as theta over t because theta is the standard Greek letter we use for angles and radians, and then t is just time, can be in seconds, minutes, hours, days, whatever. Time is not, this doesn't matter what that unit is as much, but radians has to be in radians. Okay, then we can use that formula to compute our linear speed. Linear speed will often use v to denote for velocity. And linear speed, like we talked about a couple slides ago, is just distance over time, meters per second, miles per hour, et cetera, et cetera. And we can denote this as S, which I'm using an S here because if you remember, we used S for arc length earlier. And when we're talking about linear speed in the context of a circle, we're talking about arc length or circumference. So this is S, T, again, time doesn't really matter specifically as what unit it is. And if you notice, S over T is just the arc length. That's just r theta. If you remember, we had that formula from yesterday where we said that the length of an arc was r times theta. That's all I'm doing here. We just know that S is equal to r theta, which is why I was able to make that exchange here. However, we have a theta over t here and a theta over t here. So conveniently, we can actually just substitute this theta over t with an omega. So as complicated as this may have felt, all we really need to do to compute linear speed is just multiply our angular speed by the radius. That's it. That's all you're really doing here because we're talking about that distance is circumference and hold on. So because we're talking that distance equals circumference right here, or more generally, arc length, we are able to make that substitution, and all you're doing when you're finding linear speed is just multiplying our angular speed by the radius. These two formulas will be extraordinarily helpful to you. Memorize them, learn them, they're great. Are there any other questions for now? We'll do another example. Oh, and one quick note, if you'll notice right here, when we did angular speed, we were not given radians per second, we were given revolutions per second. So another really helpful conversion factor to remember is that 1 revolution of a circle is always equal to 2 pi radians. That is always helpful to remember. Okay. So let's do an example really quick. Kind of a real world example. So we know that the Earth is 150 million kilometers from the sun, and it takes 365.24 days approximately for the Earth to orbit the sun. We want to find the angular speed of the Earth in orbit. Okay, so just to draw a picture real quick, because I think pictures are always helpful. It's really helpful to see what's going on sometimes. Here's the sun, here's the Earth. We know that this is 150 million kilometers. It's a lot of kilometers. Okay, so we know that the angular speed from this formula up here is theta over t, where theta is an angle in radians and t is the time. This is actually pretty simple in this case. We're talking about 1 complete revolution of the Earth. So our theta is just 2 pi. We're talking about how many revolutions, how many radians the Earth can rotate in a day. So we know that this is going 2 pi radians per 365.24 days, which makes sense, right? It takes the Earth that many days to complete 1 revolution around the sun. So for every 2 pi radians, the Earth travels around the sun. In other words, for every 1 revolution, it's 365 days. So we know that omega is equal to 2 pi radians over 365.24 days, which if you plug this into your calculator, you get that it's approximately 0.01720 radians per day. And that is your angular speed. You're just looking at how many revolutions or how many radians that the Earth is going around the sun per day. And we're given that information all right here. We didn't even need the 150 million kilometers because we're only talking about angular speed. We only need the radius when we're talking about linear speed. So let's find the linear velocity of the Earth in orbit. To do this, all we need to remember from the last slide is that linear velocity is just omega, which is the angular speed times the radius. That's it. So our velocity is 0.01720 radians per day times 150 million kilometers, which I believe is about 258,000,000 kilometers per day. This is an approximation. I didn't plug this one into my calculator, but you can do this math. You would just multiply this by 150 million kilometers, and it would get you that we are going that many kilometers per day. Okay, any questions on using these formulas for angular and linear speed? Okay, then if there's no questions, we're going to switch gears a little bit actually into getting into some triangle trigonometry. So some of you may have seen these before, maybe in geometry or some high school trig. So we're going to start with right triangle trig first. We call this side the side adjacent to theta. If this is our angle theta here, this side is adjacent to it because it is next to theta. I will abbreviate that as ADJ. This is the side opposite of theta because it is the side not touching our angle at all. None of this side is touching theta. We'll call this OPP for opposite. And hypotenuse is just the hypotenuse. It's the side opposite of the right angle. Just call that the hypotenuse. Okay, so these trig functions that we'll use most commonly are sine, cosine, and tangent. To find the sine of our angle theta, we just take the length of the opposite side divided by the length of the hypotenuse. To find cosine, we just take the length of the side adjacent to theta over the hypotenuse. And to find the tangent of theta, we just take the length of the side opposite of theta over the length of the side adjacent to theta. There's a funny acronym that we use sometimes to help us remember this, and it's called SOHCAHTOA. And the reason this works is because S is for sine, and then sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. That's always a good way to remember it. It's a little catchy. But yeah, these three trig functions are very, very important to remember. Always keep these in mind. We will be using them a lot for the remainder of the course, to the point where you will probably be sick of them and will have no problems remembering them. So, but if you ever forget, SOHCAHTOA is a good way to remember. Okay, so let's use just this information alone to find some information about a triangle. We want to use a calculator to find sine of theta, cosine theta, and tangent theta. So we know here's theta. So we want cosine theta, sine of theta, and tangent of theta. Right now, we only have two side lengths. We only know the hypotenuse and the side adjacent to theta. We need to know this to be able to do a couple of these functions. So how could we find it? Well, if you remember, Pythagorean theorem is just a squared plus b squared equals c squared. We can always use this for a right triangle. And if you recall, this means that the sum of the squares of the two shorter sides, so that would be the 7 and whatever this guy is here, equals the square of the hypotenuse. And the hypotenuse is always the longest side. In this case, it's 10. So let's solve for this guy real quick before we do our trig functions over on the left. So 7 squared, that's the side we know here, plus b squared, we'll call this b for now because we don't know what it is, equals 10 squared. Squaring these numbers, we get that 49 plus b squared equals 100. Subtracting a 49 from both sides, we get that b squared is equal to 51. Taking the square root of both sides, we see that b is equal to the positive or negative square root of 51. I always put plus or minus in front first because when you're taking square roots, there are always, always, always two answers. However, in this case, we're talking about a triangle that clearly has a positive side length, so we can ignore the negative and just know that b is equal to the square root of 51. That can't be simplified any further, so I will just label that side square root of 51. Okay, now using the formulas from the previous slide, we can really easily solve for sine, cosine, and tangent. So the cosine of theta is the adjacent over the hypotenuse, which is just 7/10. Easy enough. If I want to write that as a decimal, it's 0.7. Okay, sine of theta is the opposite over the hypotenuse. The opposite in this case is the square root of 51 we just solved for. And the hypotenuse is 10 again. So that is what this is. And when you plug this into your calculator, it gets us to about 0.71. And then tangent of theta is the opposite over adjacent. So that's just square root of 51 over 7, which is about 1.02. Again, these two are both approximations because the square root of 51 is irrational. If you wanted, if at 5 were asked for the exact answer, you would leave it in these forms because the square root forms are exact. These are approximations. Both will work in this class, but if it ever asks for specific, you know how to do both. Okay, are there any questions on this example? Okay. So let's talk about some special right triangles. These will come up sometimes, and they are very, very handy because they have special measurements that give them special properties. So let's start with the guy on the right first. He's a little bit easier to work with. Okay, so we know that this guy's hypotenuse here is 8, and it has two 45-degree angles and a 90-degree angle. This kind of triangle is called an isosceles triangle because it has two identical side lengths. So this side length is congruent to this side length because these two angles are the same, which means that we know that this side length will also be of length A, whatever that is. We haven't figured it out yet. So there's two ways to do this one, and I will show you both. The first way is what I like to call the geometric way. You don't even need to know any trig or anything we did on the last slide in order to do this. All we need really is the Pythagorean theorem. So in general, we know that a squared plus b squared equals c squared, right? Well, we know that this side has length a and this side has length a. So instead, we can say that a squared plus a squared, they're both unknown. We don't know what they are, but we know that this a squared plus a squared is going to be equal to 8 squared. A squared plus a squared, that's 2a squared. So we're still only working with one equation with one unknown, which is solvable. So we get that 2a squared, adding these two together, is equal to 64, which gives us that a squared is equal to 32. Just got that by dividing both sides by 2. So a is equal to the square root of 32. And just to clean this answer up a little bit, I know that 32 is equal to 16 times 2. And using laws of square roots, that's the square root of 16 times the square root of 2. If you remember, if we have multiplication under the same square root, we can split it up like that. And we know the square root of 16. The square root of 16 is just 4. So a is equal to 4 square root of 2. Also square root of 32. If you didn't, we'll practice this concept down here more with the cleaning up square roots. But if you can pull a perfect square out of whatever the number under the radical is, we can clean up the answer. So a is the square root of 32, in other words, 4 square root of 2. Cool. There was another way we could have done this, and I call this one the trigonometric way because it uses the trigonometry we just learned. Okay. So if you remember from the slide before, we know that the cosine of theta is equal to the adjacent side over the hypotenuse. Well, we don't know what the adjacent side is here, but we do know what theta is. In our case, theta, no matter which theta we choose, is 45 degrees. So we can say that the cosine of 45 degrees is equal to the adjacent, which regardless of which angle we look at, the adjacent side is A, over the hypotenuse, which we know is 8. Notice we could have also used sine here because depending on which A we look at, it could be adjacent, like this A would be adjacent to this 45 degrees, but this A over here is opposite of that 45 degrees. So the sine function would have worked as well. I just chose cosine, but notice that both could work. Okay, we want to solve for A over here. So in order to do that, we can multiply both sides by 8 and get the 8 cosine of 45 degrees is equal to A. 45 degrees is one of the special angles on the unit circle. And we know that its cosine happens to be root 2 over 2. So we get that 8 times square root of 2 over 2 is equal to A. So A is equal to 4 square root of 2, which should make sense because that is exactly what we got over here. And again, if you don't remember this from the unit circle yet, you can verify that in your calculator. Okay, now let's focus on this guy here. There is a geometric way to do it, but it's kind of messy and requires a lot more brain bending than is really necessary. It's much less intuitive than the geometric method over here of just fudging the Pythagorean theorem. So I'm just going to focus on the trigonometric way over here. Okay, so for this one, what do we know? We know that we have a 60-degree angle, a 30-degree angle, and we want to solve for B. So if we could form an equation where we just have one unknown, we'd be golden, and the unknown is B. So we want to use our unknown side and our known side. We don't know the hypotenuse, so regardless which one of these angles we choose, the 60-degree or the 30-degree, we're going to have to use the tangent function. Otherwise, we would have B being unknown and the hypotenuse being unknown, and we can't solve that. So just for sake of argument, let's work with the 60-degree angle. We know that the tangent of 60 degrees, just by looking at this, is equal to the opposite, which is B, over the adjacent, which is the 5. B is opposite of 60, 5 is adjacent to 60. Conveniently, 60 degrees is one of the important angles on the unit circle. So we actually know that the tangent of 60 degrees is the square root of 3. Just from our unit circle, we're given that the tangent of 60 degrees is the square root of 3. So the square root of 3 is equal to B divided by 5, which then multiplying both sides by 5, we get that B is equal to 5 times the square root of 3. And again, if you didn't know that tangent identity off your head, you can always check with your calculator. For now, that is totally okay. But it's really nice to know when one of those angles comes up and you just know how to evaluate it. Okay, are there any questions on these two examples? Okay, then moving on, let's do a little application of this. Okay, so a surveyor wants to know the length of a tunnel built through a mountain. According to his equipment, he is located 212 meters from one entrance of the tunnel. I'm just going to label that right now because we have this diagram and it's easy enough. So here he is. Let's just use the left entrance for now. We know he is 212 meters from this entrance. This distance here to here is 212 meters. Okay, and this is at an angle of 57 degrees to the perpendicular. So the perpendicular just means if this is how, right here, if this is how the mountain is labeled, the perpendicular is just the line crossing through it with the 290-degree angles here. So it's just making a little cross. So we know it's 57 degrees to the perpendicular, which means that this angle down here is 57 degrees because this is the perpendicular right here. Okay. Also, according to his equipment, he is 119 meters from the other entrance of the tunnel. So we can label this guy as 119 meters at an angle of 14 degrees to the perpendicular. Obviously, this drawing is not to scale, but we get the idea. Based on these measurements, we want the length of the entire tunnel. So what we are trying to solve for is the length of this guy right here. Call this our x. In order to find x, we have two triangles. We have a triangle right here, and we have a triangle right here. So I argue that if we're able to solve for the length of this guy right here, let's call it A, and the length of this segment here, let's call it B, by treating those as two separate triangles, we'll be able to find the length of the entire tunnel by just adding A and B. Okay, so let's start with focusing on this triangle right here. We know that we have an angle of 57 degrees, a hypotenuse of 212, and we want to solve for A. How would we do this? Well, we have A, which is the side opposite of theta, and we have the hypotenuse. What trigonometric function involves the opposite side and the hypotenuse? Sine. So we know that the sine of our angle, which is 57 degrees, is equal to the opposite, which we're just calling A at this point, over 212. Which, if you plug this into your calculator, well, not if we plug this into our calculator yet, but if we just multiply both sides by 212, let's start there. We just get the A is equal to 212 times the sine of 57 degrees. Now, if we plug it into our calculator, because it's a little more nice for us and will require less steps, we get the A is approximately 177.98 meters. Just by evaluating the sine of 57 degrees in the calculator and multiplying by 212. Same thing for B. We have an angle right here. We want to solve for the side opposite of it. We have the hypotenuse. We need the function that involves both the opposite side and the hypotenuse. So yet again, we are going to use sine. So we have that the sine of 14 degrees is equal to the opposite side, which we're just calling B at this point, over the length of the hypotenuse, which is 119. Multiply both sides by 119, we get that B is equal to 119 times the sine of 14 degrees. And plugging this into our calculator, we get that B is approximately 28.79 meters. So we have this, we know down here, just from the diagram over here, that our value X is equal to A plus B. So X equals 177.98 meters plus 28.79 meters, which when you add those two together is 206.57 meters. And that will be your final answer. Any questions on how I got this? Just took this diagram, made two triangles, said, okay, what information do I know? What information do I need to know? In which of our three trig functions, sine, cosine, or tangent, relates all three of those missing quantities? Okay. So let's talk about something called similar triangles really quickly. The following triangles are similar, namely triangle XYZ, similar, this is the sign we will use for similar, it's just one squiggly tilde, it's similar to ACB. We want to find the tangent of B, cosine B, and sine B. Immediately, that sounds impossible, because if we look at the triangle with B in it down here, we don't know anything about the triangle. However, we actually know quite a lot. Similar triangles, essentially, are just rescalings of one another. So I'm going to write that up. They're just rescalings of each other. And what I mean by that is you can just think of in Microsoft Word or whatever, if you take a triangle, if you have an image of a triangle, you can't stretch it or pull it or deform it in any way, but you can grow it and you can shrink it. And you can move it around, but you cannot stretch it in any way. So the integrity of the angles stays exactly the same. So what that means is that obviously angle A is equal to angle X because they're both the right angles. And if you think about if these two triangles were in the same orientation, Z right here would be in the same place as angle B, because it would be, if you think about rotating this triangle to where it looked like this one, angle Z would be in the same place as angle B. So that also means that angle B is going to be equal to angle Z, which in turn also gives us that angle C is equal to angle Y. This is all the information we need to know in order to compute the tangent, the cosine, and the sine of B, because regardless of how large these sides actually are when we rescale and resize it, the ratios stay the same. And all these trig functions we're using are ratios, ratios of the opposite side of the hypotenuse, ratios of the adjacent to the hypotenuse. So we don't care what their actual length is. We just care that the ratios are staying the same, which is why all we need is a similar triangle in order to calculate the information about this guy. In other words, we know that the sine of angle Z, because B is equal to Z, will be equal to the sine of B. And the cosine of Z will be equal to the cosine of B, etc. Okay. So let's just compute this. We know that the sine of angle B is equal to the sine of angle Z, which if we look at angle Z here, angle B and angle Z, I'm just going to label these so we know which ones are congruent to one another. So we need the sine of Z, which is the opposite side, which is 12.6, over the hypotenuse, which is 17.4. I could plug this into my calculator to get a more exact decimal, but that is also a valid answer. Similarly, we can find the cosine of B. It's just the cosine of Z because they are the same angle in a similar triangle, and that is just the adjacent side, which is 12 over 17.4. And lastly, tangent of B is also equal to the tangent of Z, which is the opposite side over the adjacent side, which is just 12.6 over 12. Are there any questions on how I did this and why similar triangles have the same sines and cosines? These side lengths will not necessarily be the same. It's not that side length ZX is going to be the same as side length BA, but the ratios between the lengths of all the sides will be the same. So the values of our trig functions will be the same. Okay, now let's think about trig functions a little bit differently. We've been talking a lot about trig functions as defined on a triangle. We have a hypotenuse, we have a side opposite of theta, we have a side adjacent to theta, and it works out really nicely. It's a beautiful picture. However, the thing with triangles is that we can never have an angle greater than 90 degrees, at least when we're talking about right triangle trig, because we already have an angle that's 90 degrees, and the sum of the values of an angles of a triangle is 180 degrees. Always, it will never be greater than 180. So we will never have a right triangle with an angle greater than 90 degrees. So what we want to do is we want to expand our trig functions. To include all angles, including angles greater than 90 degrees. You also can't really think about negative angles in a triangle because the angles don't really have a direction. You can never really think about a negative angle when you're looking at something as concrete as a triangle. So we're going to do something called superimpose our triangle into XY coordinates. And this, even though it seems like it's an extremely subtle difference at first, it allows us to do so many more things. So instead of thinking about a side adjacent and a side opposite, instead of thinking about side lengths, we're going to be thinking about points in the XY coordinate system. So we would have an X, a Y, and an R, where R is just the square root of X squared plus Y squared. We get that from X squared plus Y squared equals R squared. That's just Pythagorean theorem. It's just a solution of the Pythagorean theorem. But this will make all the difference because we could have a point over here that makes a triangle so that our theta would be greater than 90 degrees. If this were our starting point, we'd be thinking about going over here. And that would allow for an angle greater than 90 degrees, yet we'll still be able to use our trig functions. As we know from a couple slides ago, this is how we've been able to define these trig functions with a triangle. But we can't really use that when we're talking about xy coordinates because this isn't really a triangle if we think about this angle here because it is greater than 90 degrees. However, we can still use our ideas from right triangle trigonometry in order to solve for the sine, cosine, and tangent of that angle that is greater than 90 degrees, or even one that's all the way over here. Clearly much greater than 90 degrees. So when we're talking about sine of theta, for example, we're thinking about the length of the side opposite, so this guy here, to the hypotenuse. We can think of a similar idea just in the xy coordinate system. The length of the side opposite to theta, if you look at our diagram to the right here, side opposite, we just relabeled with y. It is just the y distance. It is the vertical distance on the graph. So instead of opposite, we can just think of the sine of theta as being the y value. And our hypotenuse here is just r. It's what we've been calling the radius. So the sine of theta will just be the y coordinate over r. Similarly, when talking about cosine, side adjacent to theta has been relabeled with an x. We're just looking at the horizontal distance. How far away horizontally are we from the center? Or what we call the origin sometimes, the point 0, 0. So that is just our x coordinate. And again, over the hypotenuse, which is now the radius. And then tangent of theta is just opposite, which we have decided is the y value, the vertical value, over x, which is just the horizontal distance from the center. So just by making this connection here, we are able to expand our trig functions in order to include so many more different examples, which will be very helpful when doing some calculations further on. This would allow us to compute something like the sine of 205 degrees or the cosine of negative 135 degrees, which if you remember a negative angle, we would rotate clockwise around to get to. So for example, right here, I would say is approximately positive 45 degrees. But if we went clockwise this way, this would be negative 45 degrees. So it allows us to use things like negative angles bigger than 90 degrees. It expands our range of computation to practically any angle you'll find out. Okay, now let's bring back the idea that we discussed a little bit yesterday that is super important called the unit circle. And the unit circle is just a circle of radius 1. That's all it is. It's just a nice pretty circle with a radius of 1. We'll call this angle down here theta, just for reference, when we're talking about sine, cosine, tangent down here. So because our radius is 1, life is a lot simpler. Notice that when we are on the unit circle, sine is just the y value. Now, why is this? Well, if you remember from our formula up here, sine is y over r, but on the unit circle, which we'll be using a lot, the radius is just 1. So the sine of theta is just the y value as it is y over 1. Similarly, cosine is just the x value. Because as above, we know that the formula for cosine is x over the radius. The radius is always just 1 on the unit circle. So the cosine of theta will just be x over 1. And tangent isn't quite as nice, but it intuitively makes a lot of sense. Tangent is still y over x. And you can even think about that. If you remember from algebra, rise over run is slope, y over x is slope, tangent is a slope. It just gives us the slope of this guy here. That is all tangent is. It's a little bit of a confusing idea at first, but it may be helpful later on to start to build an intuition. But tangent doesn't change, but sine is just this, cosine is just this. And if you'll notice, since sine of theta is just y, and cosine of theta is just x, we can say that the tangent of theta is the sine of theta over the cosine of theta. This gives us a very useful formula to solve for tangent later when we need to. Just a little bit of fancy vocabulary. Cosine is called the abscissa through the unit circle, and sine is the ordinate through the unit circle. These are just good words to know if they ever come up in a later math class, or if they ever come up when doing your ALEKS. Just know that these are two fancy words you can use for sine and cosine, and that tangent is just the slope of the radius. Tangent is just the slope of whatever that guy is. Any questions on this idea? Okay. As a reminder, this is the unit circle right here. I will post this on Wild Courses very soon for you all to be able to look at and study, but this is the unit circle. So for example, let's look at pi over 6. If I wanted to know the sine of pi over 6 on the unit circle, all I have to do is look at this y coordinate here, 1/2. If I want to know the tangent of pi over 6, I just do the sine over the cosine. So it would be 1/2 over √3 over 2, which is just 1 over √3. The unit circle is extremely valuable, and just from knowing these coordinates here on the outside, we get the sine, cosine, and tangent of all of these really important angles, like how I was able to use the cosine of 60 degrees in a calculation earlier and the tangent of 45 degrees. Things like that come up a lot. So just by knowing the angle values, their respective radians that they are, and the x and y coordinates they hit on the unit circle, you gain a lot of information. Okay, so let's do a couple quick examples. I want to find the tangent of 5 pi thirds. Well, from what we talked about on the last slide, we know that this is just the sine over the cosine. Oh, I'm so sorry. Charles, do you have a question?
Your last, the last slide. So are you okay with like the radical at the bottom of the denominator there, or would you rather have us clean that up?
Yes. When we actually do examples, we will clean the radical up. I should have mentioned that. I'm sorry. Normally we will not have radicals in the denominator.
Okay, just thank you.
Yes, thank you for asking. I will make a note of that. Yeah, don't leave radicals in the denominator. I just did that to show a brief example, but yes, we will talk about that more later. Thank you. Are there any other questions before I move on? Okay. So, evaluate the following. We want the tangent of 5 pi thirds. From the previous few slides, we know that that is just the sine of whatever our theta is, which is 5 pi thirds, over the cosine of 5 pi thirds. Conveniently enough, 5 pi thirds is one of the special angles on our unit circle. It is actually right here. And we know from this coordinate right here alone that the sine of 5 pi thirds is negative √3 over 2, and that the cosine of 5 pi thirds, which is the x value, is just 1/2. So it's just negative √3 over 2 divided by 1/2, which when you do fraction division, we would invert and multiply, which I will do out this time. So it'd be negative 3 over 2 times 2 over 1, inverting the fraction we're dividing by and just multiplying them across. We get that that is the negative square root of 3. Okay, let's do a similar problem. Tangent of pi halves. The tangent of pi halves is just the sine of pi halves over the cosine of pi halves. Looking at the unit circle, because this is conveniently another one of those nice angles, it's a very special angle. In fact, it is the 90-degree angle. The sine of pi halves is just 1, and the cosine of pi halves is 0. So that would mean that the tangent of pi halves is 1 over 0. However, zeros in the denominator are one of the biggest no-nos in math. This is not allowed. This is not a number. This is not a thing we know how to deal with. You cannot divide by 0. So it turns out that the tangent of pi over 2 does not exist. This will become more clear why later. You can say does not exist or is undefined. And that is because we are absolutely never allowed to divide by 0. Okay, let's look at a different one. Cosine of 17 pi over 6. Now, you may not see this right off the bat, but it turns out that 17 pi over 6 is actually bigger than 2 pi. So we are talking about an angle that goes around the unit circle more than once. So let's subtract 2 pi off of this to see if we can get an angle that we know actually how to work with, an angle coterminal to 17 pi 6, because that will give us the same cosine. So cosine of 17 pi over 6 is equal to the cosine of 17 pi over 6 minus 2 pi. We are just getting an angle coterminal. So instead of going around the circle however many times it would take us, we would just be going around this much just to get to the same point. Turns out that 17 pi over 6 minus 2 pi is 5 pi over 6. And I found that out just by doing 17 pi over 6 minus, I wanted to get a 6 in the denominator over here, so I did 12 pi over 6, multiplied both the numerator and denominator by 6. So we get that that is 5 pi over 6, just some fraction manipulation. And the cosine of 5 pi over 6 is another really fancy angle from our unit circle. That is this angle here. Again, it did not matter. We could have, the angle that was given to us was this, but that's the exact same cosine as the angle that is just this, because it lands us at the same place. They are coterminal angles. As such, their cosine will be exactly the same because they have the exact same x and y coordinate wherever they land. So just by that information, the cosine of 17 pi over 6 is the cosine of 5 pi 6th, which is the x coordinate, which is root 3 over 2. Or negative root 3 over 2. Okay, one more. Sine of negative 9 pi 4ths. So if we follow our unit circle around negative 9 pi 4ths times, that is also bigger than 2 pi. So we'd be going around negative 8 pi 4ths times. We'd be going around like, didn't work. So first time going around, that would be negative 8 pi 4ths, and then we would go one more and land here, which is the same as negative pi 4ths or the same as 7 pi 4ths, however you want to say it. So for sake of just consistency, let's say that it's the sine of 7 pi 4ths, which is also the same as the sine of negative pi over 4, depending on how you want to look at it. It can really help sometimes to just draw these circles walking around the circle negative 9 pi 4ths times in the clockwise direction until you get the hang of it. And then just by looking at the circle, we know we land here. And the sine is the y coordinate of our terminal ray, which is just negative square root 2 over 2. Are there any questions on this idea of just using the unit circle in order to evaluate these values of sine, cosine, and tangent? Okay. Then let's do another example. Suppose we have an angle theta that is in standard position, meaning its initial ray is on the positive x-axis. And its terminal side, in other words, the side of the angle, wherever the angle ends, the other one that is not the initial side, intersects the unit circle at that point. So let's draw this. We have our unit circle here, and we have some angle theta. We know that theta is going to end in the first quadrant because this is a positive x value right here. And this is a positive y value. So we know it's going to end somewhere over here. We don't know where exactly, but we know it's going to end somewhere over here because positive x value, positive y value. Here's, oh, that was not. Here's our terminal ray right here. Here's the initial ray down here in standard position on the x-axis. This is the angle theta. And we know that this point right here, which our angle intersects the unit circle, is 7/25, 24/25. We want to find the exact values of cosine and tangent. Well, turns out we already have all of the information we need. We have our x value, we have our y value, and because we're talking about the unit circle here, we already have our radius, which is going to be this guy right here, which we already know has length 1 because the unit circle has radius 1. So, using this information, we know that the cosine of theta is just our x coordinate, which is 7/25. And then the tangent of theta is just the y coordinate over the x coordinate using those formulas from a couple slides ago, which is just 24/25. Nope, not 24/25. Yes, 24/25 over 7/25, which when we would divide fractions again, we get is just 24/7. Any questions on how we did this one? For these, I would honestly just recommend drawing a picture because it can look like a lot of information and it doesn't really make sense how it all relates until you draw it out. That would be my biggest advice for these, is just always, 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 always draw a picture. Okay, let's do a couple more examples before we wrap up for the day. Let's ramp it up a little bit. Okay, suppose that -√7/3, y is a point lying in quadrant 2 that lays on the unit circle. We want to solve for y. I don't really know what to do here right off the start, so again, let's just draw a picture. Let's draw some axes. And I know, if you remember, this is quadrant 1 right here. This is quadrant 2. This is quadrant 3, just walking around counterclockwise, and this is quadrant 4. And we know that this point is somewhere in quadrant 2 on the unit circle. So let's draw our unit circle. Here's a point, it's in quadrant 2. We know that the x coordinate is the -√7/3, and we don't know what y is. But we want to solve for y. We know that the length of this guy right here is 1 because we're laying on the unit circle. So what could we do? Well, what we've learned a lot about today is triangles. Let's see if we create a triangle, what information we have. If we think about this guy right here is maybe being a triangle, what information could we pull? Let's extract it. Okay. So looking at that triangle there, let's just draw it out. We know that that's a right angle down here. We know that the radius has length 1, and we know that the x coordinate over here is -7/3. So we know that the x distance from the center to where the triangle ends is -√7/3. So that means we know the length of this guy down here. We know that the length of that side is the √7/3 because that is how far out our x values goes in order to get there. And we want to solve for the vertical distance. We want to solve, in other words, for this side length right here. Let's call it y. Okay, so what do we know where we have a right triangle with 2 known side lengths and 1 unknown side length? Pythagorean theorem. Beautiful. All we need. We don't even need sines, cosines, and tangent. We just need the a² plus b² is equal to c². Because we have 2 side lengths in a right triangle and we want to find the third one. That's all we need. Okay, so plugging things in, let's say we have the √7/3² as our first side plus y². We need to solve for y. It's equal to 1², which is 1. √7/3² is √7² plus y² equals 1². So 7/9 plus y² equals 1. which gives us that y squared subtracting a 7/9 from both sides is equal to 2/9. Therefore, y is equal to the positive or negative square root of 2/9, which is just equal to the positive or negative square root 2, because I have to leave the 2 alone, over 3. We can take the square root of 9, and the denominator of that is just 3. Now we have to think about, because we know it's in quadrant 2, is it the positive square root of 2 over 3, or is it negative square root of 2 over 3? Which one is it, and why? Well, because we are in quadrant 2 over here from our diagram, we can see that all of the y values in quadrant 2 are positive because they're above the x-axis. All the y values in both quadrants 1 and 2 will always be positive. So, as a result, it is going to be the positive option over here. Y will be equal to the positive square root of 2 over 3. If I had given you in the problem that this point was a point in quadrant 3, then it would be the negative option. All of this information up here was necessary because there would have been more than one answer had you not known what quadrant the answer lied in. Are there any questions on this idea or anything else in this example? Again, just drawing a picture and thinking about the information you're given, extremely helpful. Okay. Let's do a quick summary of some of the trig functions we've learned and talk about a couple new ones briefly. Okay, so far we have learned cosine, sine, and tangent. These are 3 we've already talked about. And turns out we talked about tangent in the context of the unit circle. However, tangent will always be the sine of theta over the cosine of theta just by fraction division, because we could do y divided by r over x divided by r, which when we do fraction division is just y over r, invert and multiply, times r over x. The 2 r's will cancel and we will be left with y over x. So I mentioned that tangent is y over x in the context of the unit circle. This turns out to be always true. It's a nice fact, but these 3 will be very important to remember. However, we can also talk about their inverses, or what I like to call the 3 reciprocal functions. And if you remember what a reciprocal of a fraction is, all that is we are just flipping that fraction upside down. That's all we're doing. So secant of theta instead of x over r is r over x. If you're given the cosine of something, you just take 1 divided by that cosine. It gives you the secant. Same for cosecant. Cosecant is the inverse of sine. I know it sounds a little backwards. We want cosecant to be the inverse of cosine and secant to be the inverse of sine. Unfortunately, it doesn't work that way. But secant is the inverse of cosine. Instead of x over r, it's just r over x. Cosecant is the inverse of sine. Instead of y over r, it's r over y. You can just always use these 2 formulas. And then cotangent is the inverse of tangent. Instead of y over x, instead of looking at the slope, we're looking at x over y. And if we have the information of sine and cosine again, instead of doing sine over cosine, you just do cosine over sine. Same idea. Okay, are there any questions on these? I'll just make a note that this is the inverse of cosine. This is the inverse of sine. And this is the inverse of tangent. And we will refer to these as the inverse functions or the reciprocal functions, depending on the context. Okay, I think this is actually a good stopping place for today. We will get into some more examples involving these inverse functions tomorrow, but for now, I think this is a good place to stop. Yeah, you have an Alex due either tonight or tomorrow on angles and radians. I don't remember which off the top of my head, but please do those. I meant to make an announcement at the beginning of class and I forgot. I have to postpone my office hours today until 2. So instead of right after class, I will be having them from 2 to 3. If that does not work for you or you need extra help, email me and we can do any other time. But otherwise, that's all for today. The course packets are still not in the bookstore. I'm working on that. I will let you know if that gets figured out. Otherwise, I will see you all tomorrow or in office hours later today. Thank you.